Welcome to the second half of session 10 on motors. Last time we looked at a whole bunch of applications of the commutator type of motor. All that power hand tools that it drives, kitchen appliances, like a mixer. It's used in vacuum cleaners. We didn't talk about that. And today what we want to do is take a look at how did we get to the commutator type of motor, which is so common in so many devices, and are there improvements to go beyond the commutator type of motor? So let's start with some really basic and kind of fun things to look at. I learned about this motor from one of the teachers I was doing demonstrations for, is Terry Angelbeck, 7th grade science teacher. She's with Evergreen School District in the city of Vancouver. So let's just run this. It's kind of fun to watch. It's just a coil wire and a battery. Let's take a look at how this all goes together real quick. And you could build this yourself, you know. None of these parts are that hard to find. Let's start with the base here, a little block of wood. There's the battery kind of clamped in place. I use this heavy gauge, well, not real heavy, but it's like a number 12 copper wire, which is pretty common, but not everybody has access to that. So you can use other types of things. You can even use paper clips. And what these wires do is they convey the electricity to where the rotor is going to be. And they support the rotor. These sit on those little U-shaped things there. Those are the bearings. Now you may want to make it a loop so this doesn't pop off. I have made it that way so that I can put other coils on here easily without having to pull things apart. The other thing you need is a little magnet. You need a magnet where it's a north above and south below, or vice versa. Not end to end. We don't want a north and a south. We want the top to be a particular polarity, so that you have a magnetic field coming upward, cutting through the coil. Okay? The coil has to react to that magnetic field. Let's take a look at how this is built. This is made out of magnet wire, and you go around and around and around as much as you want. And then when you're done with that, you take the ends of the magnet wire and twist them around, kind of bailing it, okay, bundling it, and have the ends stick out about 1 inch. And the next thing you have to do, remember this is magnet wire which is insulated, and you need to remove some of the insulation, not all of it. Remove insulation from one side of each end. Do one side of each end, but not the other side, so that as this rotates, it turns the coil on and off every half a turn. If you don't do that, it will be on all the time, and it will go into a position and it will just kind of stop. Okay? It'll just stop. So you need to have it insulated on half of the turn. Now if you don't have magnet wire, you can use ordinary wire. In that case, probably the easiest thing to do is strip off all of the insulation on one side, but only do the insulation, strip it off, half of it on the other side. And look at how I've got this sitting. I've got the coil vertical, and that's where you trim the insulation off gently, but you want this side to stay on. Now I suppose if you end up ripping all the insulation off, you might be able to paint half of half of this side so it's insulated. I haven't tried that yet. I haven't tried paint. So let's see how this works. I think he goes faster the other way for some reason. There we go. That's something you can build yourselves. Now, we learned in session 9 that when we have a coil of wire like this, which is an electromagnet, and we put steel in it, we multiply its effect substantially. It becomes a stronger electromagnet. So let's take a look at another little homemade motor and see if you'd like to build something like that. I just bent that wire. So let's run one. I'm going to show you how it works. It doesn't seem like it's going very fast because of the way cameras and lighting work together. You can hear that. All right. Let's take a look at what's spinning. It's kind of like this thing right here, but that's probably a little confusing right now. So let's start from scratch. We need this little wooden dowel, or you could wind a bunch of masking tape if you want. We need the dowel. I'm going to take a nail and get rid of the head. If you leave the head on, you're going to have a hard time getting a bearing that works nice. So you want to take the head off, either cut it or grind it off. And now we need a core. Now there's lots of ways of making a core. You can use a bundle of steel wire, just cut a whole bunch of wire about that long, and I would do a lot more than that. It's not much fun, that part of it, but that could be your steel core, or you could cut up sheet metal. Now, I was kind of sloppy with this. I was in a hurry. You can cut up little pieces of sheet metal. Be careful you don't cut your hand on the sharp edges. So that could serve as a core. My favorite, if you can find one, is the parts of a transformer. Transformers have this kind of a core. They have this E section, a whole bunch of those, and a straight section, and they alternate, and there's a coil of wire right in the middle. So it's a little bit of effort to take one apart, and you have to be careful you don't bend stuff. But if you're lucky enough, you'll end up with something that's just perfect for building a motor. Now I'm going to show you that this is laminated. Can you see the... Give it a second to focus there. You see it's bands of steel. It's little pieces of steel. It's not just a block of steel. And that we would put on here. You may need to glue it or figure out some way to attach it to the shaft. So here's our core, and this is where we're going to put something called a commutator. Then you take, so we've got that, and then you take your magnet wire and leave about 3 or 4 inches out here. Maybe tie it to the shaft so that you can start winding without it following you out. Tie it on there and then start winding the magnet wire and go across, come back, and then keep going. Keep winding across to here. Don't go too far, too close to the edge, it'll start unraveling. And then come back to the middle and then leave another 3 or 4 inch piece here. Now while you've got that kind of held in place, wrap your magnet wire with some kind of tape to keep it from unraveling. Now you're pretty close to this, and what you do with those 2 wires is you can strip them first of insulation, because remember this is magnet wire and it's insulated. So you could strip the insulation off first, and then holding it in this position. This is the position that you want to be working, I'm sorry, let's hold it this way. Got with this, the long way down here, you want to have your uninsulated segment of wire go back and forth, back and forth, back and forth, close together. On this side for one of them, and on this side, same way, back and forth for the other one. And you can hold it in place with some kind of good adhesive tape, like this is like Gorilla Tape, so it'll hold it pretty well. And now all the insulation is gone, so if you were to hook up electricity to either side there, this will become a magnet. And that is how this motor works. There's the commutator, and there's the electromagnet. It has a steel core. And what the commutator does is it keeps the pole that's up here between these two stationary poles the same polarity. If we want it to go in this direction, I think that's the direction it wants to go. No, is it? Which way do you want to go? Yes, it wants to go that way. That means when I hook this up, this is a south pole. But when it goes to the other side, I want it to be a north pole. And I want this one to be a south pole. And that is what the commutator does. It reverses the direction of flow every half a turn. Every half a turn, it reverses the direction of flow. So it keeps going. You remember we had that issue with this wire. We needed to have only one side trimmed off so that it would keep going. It needed to go on and off at the right time. And here, on this one here, we are reversing the flow at exactly the right time so it'll keep turning. Now, about 120 years ago is when they came up with the conventional commutator type of rotor. Let's turn you off. Let's compare the two here. They both have a commutator, they've got the windings, and they have a steel core. That little wooden block in there is just a convenience for tying the shaft to the core, okay? You could do that on your motor too. So in this case, the commutator reverses the direction of flow every half a turn. But in this motor, the winding is very sophisticated, and there are multiple windings here. There's one for every pair of copper segments. And as this rotates just one segment, there's an adjustment to the flow of electricity, and it always keeps, let's say, the north exactly in one position and the south exactly in one position here, just barely varying as it goes segment by segment by segment. What that does is it places the north and the south of the rotor in exactly the perfect position to produce the maximum amount of rotational force, torque. Okay? All right. Now, what if we didn't want the commutator? What if we wanted to just energize a coil and move the magnet? That way we wouldn't need the commutator, the brushes, the noise it makes. Let's check that out. Here is one of the coils we used a while ago, and we'll hook that up right here. Now, if I, let's see, If I push on, I've got to turn this on and keep it on. In order for that to keep going, I need to turn the coil on and off. If I don't, that's all I get. Okay? I'll put it anywhere here, and that's all I get. In order to keep it going, I need to provide a way of turning this on and off, on and off. And what I've done is I put this little switch in here, and this switch is activated by a little cam. That's an oblong oval there, and it turns it on and off at exactly the right time. Now, that switch would wear out rather rapidly, probably be a little bit noisy, but we've already solved that problem. Solid state physics has taken care of that problem. Let's take a look at this fan. This is a fan that's typically used for cooling of different kinds of electronic equipment. There's one or more of these in your desktop computers. Let's look at what's inside. Inside is a north, north, south, south magnets along the ring there. Let's zoom in a little bit on that. There. Okay. Now, those magnets interact with these 4 electromagnets. Those are just electromagnets made of magnet wire. Let's go back out a little. And so this will be a north and a north, this will be a south and a south, and they'll interact with these 4. The thing is, those have to change exactly at the right time in order to keep this rotor spinning. How does it do that? Well, there is a sensor right there. Let's zoom in a little bit. There's a sensor right there. And notice it's between these 2 electromagnet poles. So when this rotor goes by, that sensor knows exactly whether it's a south pole or a north pole sitting there. And if we want the rotor to go in that direction, and let's say the north pole is sitting right here, we would want to make this a north pole and that a south pole. And since there's a north pole sitting here, there would be a south pole sitting right here, and this is a south pole. We'd want to make that a south pole and this a north pole. And that would be all, each of those would be in the same situation. The pole that was sitting there would want to be pushed in that direction. So that sensor communicates to the digital circuit that's behind this little plastic what the position of the rotor is, and it turns on the power in the right direction to energize these electromagnets to the right polarity, and that's what causes the motor to spin and the fan to cool. Now here is a motor, or a fan, just like that. Only this one isn't broken. It runs. Okay. Well, I hope you have enjoyed this session, and next time we will be looking at where electricity comes from. We've got all kinds of stuff we have to run. We need to know what's the source of electricity. So I'll see you next time.